All right. Let's talk about some light. So have you seen this before? You like it? You like the magnetic spectrum? This is the spectrum of light. You've got light is energy, is a form of energy, and it can be described in a few different ways. We can talk about its energy using the regular energy units, which I realize we didn't go over since we didn't do chapter 6 yet, but we will. But joules is basically the unit that we'll use mostly as the unit of energy. So we can talk about light in terms of its energy. We can talk of light in terms of its frequency. What does that mean? You know what frequency means?
How many times it like goes back and forth in like a given amount of time?
Yeah, so frequency is in units of hertz, and hertz is, actually, draw this here. Hertz is also known as inverse seconds, or 1 over second, which, what does that mean? 1 over a second? It really means cycles or occurrences per second. So how many times does something happen each second? That's what a hertz is. So when we talk about the frequency of light, what are we talking about happening per second? What is light doing a certain number of times per second? Yeah, it's completing a wave. So we know that light looks like this. And if we look at just this section of the wave, we can cut that anywhere we want, but when it completes an entire wave, when it gets back to where it started, that's called 1 wavelength. So, and we could talk about like going peak to peak or valley to valley or middle to middle, however you want to cut that is fine. So when it completes 1 wavelength, and so when we talk about hertz, we're talking about how many times is it doing that per second. So the frequency is how many times the light is doing this per second as it goes through a particular point. All right, so then let's think about what that means. If you've got a wave going like this, okay, and you're trying to measure how many times, like let's say the peak, how many times the peak is crossing a certain spot each second. If the wavelength is longer, is the frequency going to be smaller or greater? In other words, if the wavelength is long, if it's a longer distance between peak and peak, are there going to be more peaks crossing every second or fewer peaks crossing every second? Fewer, because it's longer, right? Does everybody sort of see that? If you've got a wave that's like the length of the table, and each second it's going, and then it's the length of all the way to the end of the table, it's going to be about half as frequent that it passes that. So that's why what you see here when we talk about light, we talk about it in a couple different ways. We talk about it in frequency, we talk about it in wavelength, and we talk about it in energy. And we're going to talk about how to associate those with each other. So first, we need to know that the relationship between, see if I can get this on the same screen. Probably not. So first of all, this is a typo from the book. Frequency is not lambda. Frequency is the Greek letter nu. Looks like a V, but it's not a V, and that's actually important because V is velocity, so that's nu. Wavelength is measured with Greek letter lambda. So the product of the wavelength and the frequency is the speed of light. So let's write that. And what is the speed of light? Yeah. So that shows us how wavelength and frequency are always related. If wavelength goes up, frequency goes down. Now, in order for this to work, we need to watch our units here. Speed of light is meters per second. So we have to use the wavelength in meters and the frequency in hertz. hertz is 1/seconds in order to get that to work. We'll often talk about wavelength in meters, but also in like nanometers, things like that. So if we look back up at the spectrum, you'll see why that is. So here's the entire spectrum of light. At the very low energy spectrum, low energy end of the spectrum on the left, you've got things like radio waves. So how radio, TV, that kind of stuff is transmitted through the air is by sending out this special type of light called a radio wave. And that's light that has really, really big wavelengths. Look at the wavelengths on that light. This is in meters. So when we talk about radio waves, we're talking about 1,000-meter, kilometer-sized waves going through the air. And so that means that their frequency is going to be pretty low, relatively speaking. I mean, this light is still really fast, but the cycle, there's going to be about 10,000 cycles per second going through a particular point. Then as we move up in energy, the wavelength goes down. So the waves are getting shorter and shorter and shorter. And there's various reasons why we use different parts of the spectrum for various applications. A lot of it has to do with how far they can travel without breaking down. So the low energy waves like radio waves are not absorbed by most materials, by most like atoms and molecules. And so they can travel a long distance, whereas things like infrared light, ultraviolet light are absorbed by matter. All right, so you can see some of the basic stuff like the microwave region. So when we talk about a microwave oven, this is what's happening. Your food's being bombarded with light in the microwave spectrum. Microwave spectrum light is special because well, at least that particular one, like in a microwave oven, it causes water molecules to rotate. So that's what a microwave oven does, is it causes the water molecules in your food to rotate, which creates heat. So there is nothing dangerous or scary about microwave ovens. They're not nuclear radiation, as some people sometimes think. All they're doing is making the water in your food spin around. They can overcook your food. They can make it hot or taste weird maybe just by being too hot. But it's not like putting some sort of dangerous thing into your food. And you can stand in front of it also. It's not going to hurt you. If your face gets really hot while you stand in front of it, then you should get a new microwave and you should stop standing in front of it. Okay. Moving on in the spectrum, we've got the infrared part of the spectrum, which you can't see. This is the light that's used in things like remote controls. Also, it's very important for the greenhouse effect, which keeps the planet warm. Also, too warm, nowadays. But without that infrared light bouncing off the greenhouse gases in the atmosphere and being reflected down, we would be too cold to survive. And then right here in this little pocket, you've got the visible light. So this is light that we can see from red to purple. And here are the wavelengths of the light that we can see of the spectrum. So that's in nanometers. Nanometers is a convenient unit for talking about visible light, ultraviolet light, infrared light, because that's makes nice whole numbers in the hundreds. But we have to be good at converting nanometers to meters so that we can still do these equations and things like that. And then the higher end of the spectrum, you have ultraviolet light, X-rays, gamma rays. This is known as ionizing radiation because that type of radiation has high enough energy that it can knock electrons off of things. That's ionization, is knocking electrons off of things. And that's why we call that kind of the dangerous area of the spectrum, where you have to be a little bit careful so that you don't get too much of it. That's where things can cause cancer and stuff like that. All right, so that's the spectrum. So we can always solve for frequency or wavelength if we're given one or the other based on this equation. All right. So let's move on and get to some of the weirder stuff. I'll just show this picture. We don't have to put it in the notes. Waves can interfere with each other. Light waves can interfere with each other, just like water waves can interfere with each other, and they make that connection in the book as well. There's two ways they can interfere, constructively and destructively. So if you have waves that are in phase, that means their peaks are lining up. When they add together, they're going to make bigger peaks. Notice what doesn't change. The wavelength doesn't change. The frequency doesn't change. The amplitude changes, the size of the wave. Okay. If they're out of phase, the opposite thing happens. They cancel each other out. So you end up with what we call destructive interference, meaning that you just flatten the wave out. All right, so when we put this stuff together, some interesting things happen. Waves and, yeah. Speed of light. Yeah. So imagine now waves passing through a small hole, a slit. You've got those lines represent the crests of the wave. So it's like you're looking down on the waves. And they're going through this thing, and then they go through this little hole. What happens is the waves kind of spread out in this way. They do something a little bit like that. And if you've ever, I don't know, seen like a break wall at the ocean or at the lake or something, and the waves are coming through, you can actually see this happen. You can see this happen in the water. We'll talk about particles in a second, but yeah.
So does the entire wave go through the hole, or does some of the wave bounce off and go through?
You're kind of seeing, what this is really showing is a bunch of waves all together. And so some of them are kind of going this way and some of them are going that way. So it's kind of changing the direction of the waves. That's known as diffraction. Particles wouldn't do that, right? If you shoot a bunch of little rocks or something through at somewhere with a hole, some of them would just go through, continue on their path, and other ones would just stop. So they wouldn't get diffracted in the same way that the light does, or that waves do. If you do this 2 times, and we're going to talk about what some of the consequences are for this, because it gets a little weird. If you do this 2 times, you're seeing that diffraction at each slit, and then those waves are interfering with each other in different ways depending on where they are. So you end up with this pattern where some of the waves interfere constructively and you get peaks, and some of them interfere destructively and you get flat. And if you were to like measure this on a film with light, you'd basically see dark spots where you had destructive interference, so that light is gone. And then you'd see bright spots where you had constructive interference. And based on that pattern, you can make some conclusions about the spacing of the slits or the layers, and there's various things you can find out from that. We're not going to be concerned with that right now. All you need to know is that that happens, and that's different from what would happen with just particles. Okay. So for a long time, it was assumed that waves and particles were different. That waves do their wave thing where they get diffracted, and particles do their particle thing where they travel straight through. There's a little bit of a problem with that, though. Okay, and the problem comes up with something called the photoelectric effect, which Einstein was studying. The photoelectric effect is what happens when light hits a piece of metal. When light hits a piece of metal in an evacuated chamber, it can cause electrons to shoot off of that piece of metal. Now, we don't like see that kind of just out in the open because the electrons that shoot out get absorbed by the air. So that's why you need an evacuated chamber. But if you set up a thing like that, the light hits the metal, the electrons come off, and then you can actually measure the current that's created by the electrons moving. Because moving electrons is a current. So you can detect that when light hits a metal surface, electrons come out. But what was really unusual and troubling about that is that this is kind of what happens. So we've got frequency of light, rate of electron ejection. So like how many electrons are being ejected. So let's say you had, there's no numbers here, but let's just throw some in there. So let's say you had like some light. Blue light has higher energy than red light, right? So you separate your light using a prism, and you shoot red light at your metal. And let's say red light is down here. Let's say blue light is up here. So you shoot your red light at the metal to eject the electrons, but nothing happens. And you shoot more red light at it and nothing happens. And you shoot more red light at it and nothing happens. And you have a super intense amount of energy of red light being shot at this metal and no electrons are being emitted. So then you switch it to blue light, just a little bit of blue light, really dim blue light, and all of a sudden the electrons are ejected. The red light didn't do it, but the blue light did. And now it works like you'd expect. The more light you put in, the more electrons get ejected. So there's this threshold frequency where any light that's lower energy or higher wavelength doesn't eject the electrons, even when you put a ton of it in. And the consequence of that is that there must be a particle of light that has, or something we can call a particle of light, that has enough energy to bounce this electron out of the metal. And so even just one little piece of light, if it has enough energy, could do this. And this is the beginning of what we call quantum mechanics. Because now, instead of talking about light as just this wave thing, we talk about it as these little packets. Anybody know what the little packets are called? No. Photons, yeah. So a photon, we can think of as a little packet of light. And so even when you just have one of those little tiny packets of light, you can eject one electron. If you had 2 packets of light, you could eject 2 electrons. If you had 3 packets of light, you could eject 3 electrons, and so on. But each packet has to have enough energy to do that. And if you have a packet with too small of energy, then it's not going to work even if you bombard billions and trillions of those little packets at the metal. So that's this idea of this threshold frequency. And the only way this can really be explained is through those packets. That's the beginning of what we call quantum mechanics. Quantum means to count, so there needs to be this like little packet of energy to get this electron out. From this comes a really important equation that relates the energy of these little packets of light to the frequency. So E is the energy of a photon. Nu over here is the frequency of the light in the photon. And then this H is nu. This is a constant that relates the two. It's called Planck's constant. Should we get the right exponent here? 6.626 times 10 to the minus 34 joule seconds. You don't need to remember that number. It'll always be given to you. But this is how we can relate what type of light is it? Is it red light? Is it blue light? Is it infrared? Is it ultraviolet? Is it radio? Whatever. What kind of light is it? And how much energy is each individual photon of this light going to have? We can also rewrite that using the equation that we saw up here that relates frequency and wavelength. And so we can talk about energy in terms of wavelength by knowing that the product of the wavelength and the frequency always is the speed of light. So that's just a way of rearranging that by solving for nu in the other equation that we saw up there. All right, so in this way, we can calculate the energy of these new things called photons, these little packets of light. And so this got people kind of thinking about, well, what's going on here? Why is light behaving? If light is behaving as these little packets, well, maybe there's a couple things going on. Maybe this idea of having waves and having particles that are two separate things with separate behaviors isn't quite right. So the next thing that really wasn't understood well until these ideas was the atomic spectra. So let's look at one of those, which we saw yesterday. This is what you did with the stuff in lab. So if you excite individual elements and allow them to release their energy through light, they don't just make a white light spectrum like you see below, which is what happens when you simply heat something up. So when you energize these elements, they make these line spectra. They make these individual lines. And that kind of goes with this idea of these packets, because we're saying that electrons can only move in an atom in very particular and specific ways. So they're not continuously variable. And that brings us to something that you've probably seen before, which is the Bohr model of the atom. Let's not put that there. Let's put that down here. Well, the Bohr model was kind of the first thing to explain this idea. That if you had individual little spots that the electrons could sit in, then if they jumped from spot to spot, that would give rise to these different lines. And elements that had more electrons would have more possibilities for electrons to jump around, and therefore more different lines. And that's what we saw. And so this works very nicely for the hydrogen spectrum that you can actually, and Bohr actually developed an equation where based on which level the electron started at and which level it ended at, you can predict where those lines are going to be, and it works. And that's always an exciting thing about a theory, is that it can be predictive of what we actually see in real life. So what's happening here is we have what's called a ground state atom. Ground state means all the electrons are as close to the nucleus as they can be. When you put them in that lamp thing that we saw yesterday, which I guess isn't here anymore, you put them in that lamp thing, you're putting a lot of voltage, a lot of energy into those atoms. What that does is it forces the electrons to the outer energy levels. It excites the electrons, they bounce out to the outer energy levels. Then they relax back down again. And when they relax, they emit that energy out. And emitting that energy out is what is the light that we see. So every time an electron relaxes from this level to this level, a photon shoots out of that particular energy. And this quantization of energy levels, the idea that the energy levels in an atom would be discrete and not continuously variable, was a big deal and a big change from what had been thought before. So while we're talking about that, let's actually look at that equation before we get into the other weird stuff that comes later. So Bohr came up with an equation that looks like this. He said basically that the energy of any given level is dependent on which level it is. And the higher the levels are, the higher the energy. But the difference between the levels is going to get smaller and smaller as you go from lower to higher. So that comes up with, he comes up with a constant that relates all this stuff. And again, this only works for the hydrogen atom. So 2.18 times 10 to the minus 18 joules times 1 over n squared, where n is the energy level. So you'd say, like, okay, there's an energy, like the way these are shown here, there's an electron on the 5th energy level, n equals 5. So we plug 5 into that equation, solve it, and that's the energy of that electron. Now that by itself isn't super useful because it's its energy, whatever. What we use it for, or what we can use it for, is to describe the spectrum by looking at the difference. We can say that the change in energy as we go from, let's say, N5 to N1 is going to be the difference in those two energy levels. So it's going to be the energy from level 1, or here, let's do it this way. So in this case, that's E1 minus E5, because it's going from 5 to 1. So final minus initial. Which order you subtract them in doesn't really matter. It's just going to change your sign. So one's going to be negative or versus positive. So we can plug this in the equation. We're going to call this constant B, because I don't have to write it a bunch of times. So that's going to be B times 1 over 1 squared minus B times 1 over 5 squared. Of course, as you know from math, you can distribute this. So let's solve that. One over 1 squared is, of course, 1. 1 over 5 squared would be 1 divided by 25, so 0.04. So 1 minus 0.04 is 0.96. And we multiply that by Bohr's constant here. And we get 2.09, or it's negative, so negative 2.09 times 10 to the minus 18th joules. All right. So what can we learn from that information? Yeah.
Energy levels arbitrary? Are they?
Kind of, yeah. So they're developed based on the spectrum, because the spectrum is experimentally verifiable. And so we're going in the opposite direction, but what they would have done is look at the light, figure out the energy from the light, and then work backwards to put these steps in there to get these numbers. But yes, that's right. There's no like it comes from experiment. It doesn't come from, well, that's not entirely true, but you're right. It kind of seems arbitrary. All right, so what do we do with this information? We have an energy now. We have an energy, and we know from what we just talked about that we can talk about photons based on that energy. So if we see light coming out of an atom, we can look at the energy of the photons of that light and know something about what type of light it is. So we can take that number and plug it into the photoelectric equation, which relates energy and the type of light that it is. In this case, we're going to take that energy. We're dropping the negative here. The negative just shows us that the energy is emitted. If it were absorbed, it would be positive. But the actual absolute value, the magnitude of the difference, stays the same. We know hc, that's a constant, and we can solve for lambda. All right, so this is going to really help if you have a scientific calculator that can do scientific notation a little better in this case, but we can at least estimate it here. So joules cancel, seconds cancel, we're going to end up with meters. If you don't have a calculator that can do this, here's what you do. Multiply the non-scientific notation parts, so 6.626 times 2.99 divided by 2.09. So it's going to be 9.48. And then to get the exponents, since they have the same base, we can add and subtract. So 10 to the minus 26 plus, or times 10 to the 8th is going to be minus 26 plus 8, which is minus 17. 10 to the minus 17. Wait, is that
Wait, why
right?
is it 6 and 10 to 26?
It's 34, 34. Yeah, I was going to say that doesn't look right. I don't know where I got that 26. I'm sorry. Try that again. Minus 34 plus 8 is going to be 26, right? Minus 26. And minus 26 divided by 10 to the minus 26 divided by 10 to the minus 18 is 26 plus 18, or minus 26 plus 18, which is going to be minus 8. So that's 10 to the minus 8 meters. Is that right? Somebody check that? Okay. All right, so this tells us that when an electron jumps from the 5th level to the 1st level, we emit light of that wavelength, which is about 94 nanometers, 95 nanometers. So that's in the UV. That's not exactly what's in the diagram there. So that's not light that we can see, but that's light that we can detect. So this tells us that when those electrons do that, they emit UV light of exactly that frequency. And that's what happens. So working backwards, if you were in Bohr's day, they would have detected that light and then used that to calculate which levels they would have switched from. And that's something that you can do in your lab, that it asks you to do in your lab. So like here's some other examples. If light goes from the 5th to the 2nd level, and you plug in 5 and 2, you come up with 434 nanometers, which is that violet light that you see. You can also do it backwards. You can plug in the number in the equation, solve for which level it goes to. You can't solve both of them, but assuming that it's like staying on the 2nd level at the end, you can say it's going from 5 to, or which level is it going from to get that type of light. We'll do some practice problems like that, and you can figure out what type of light it is. So that's how the hydrogen spectrum comes up. And so at this point, we've got two pretty interesting ideas that have really changed the way that we explain things. One, that light is in these individual packets, and that two, those packets have the energy to move electrons in atoms between these very specific levels. Okay, so here's where it gets a little bit weirder. We're gonna see if I can find a video for this one. Uh-oh. Okay. Watch this video with this weird guy. But I have to change the sound because it's not. Yeah, it's trying to make it.
And here we are, granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls
So this is going to be a
of
little review of
matter,
what we just talked about with particles
if
and
we
waves.
randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of Higgs. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently.
That's okay. So now it goes a little off the rails, but this is not a great video for a few reasons. But it's a good video. Like, I wanted to show, I think the pictures and stuff are good. And the effects that they talk about are true. Those are actually happening. So this is some of the real weirdness of quantum behavior is when you talk about a particle, an electron, being shot through these slits, it's behaving like a wave. And so what's special about the electron compared to, say, a marble? Anybody?
It's charged.
It's charged, but what do you think could cause it to behave like a wave? The weird thing about this answer is it's not special. Marbles, baseballs also behave like waves. The only difference of the electron is it's much smaller and it's traveling much faster. And the smaller something is and the faster it goes, the more its wave properties become apparent. And so one thing we're going to look at in a second is how we can actually measure the wavelength of something like a baseball. Now, where this video is wrong, we should talk about here. So all this stuff is right. The electron is actually behaving like a wave, which means even an individual electron, which we think of as a particle, is interfering with itself in these slits. What's not quite right is this picture here. So what they said in the video is when you watch it, suddenly it goes back to behaving like a particle. That kind of, and therefore that means the electron knows it's being watched. That's not quite right. What really happens is you can't watch an electron entirely passively. So the only way you can detect it is something like this, where you have a laser that's bouncing off the electrons as they go through. And so in that case, what the better way to say that is you can't measure it without also interfering with the process, without changing it. So far we haven't come up with a way to measure it without interfering with it. So it's not that like the electron is doing some magical thing. It's still definitely weird, but the measurement isn't purely passive as part of that also. Okay, so what this means overall then is that not only is light acting like a particle with these little packets, these little photons, but particles are also waves. Particles can act as waves. We can calculate that through something called the Broglie wavelength, which is our way of quantifying this. So he determined that the wavelength is equal to that constant again, Planck's constant, divided by the mass times the volume. So m is mass and v is volume. So things that are really, really small and traveling really, really, or no, that's not volume, I'm sorry. Velocity, sorry. Back in the gases chapter. All right, so things that are really, really small have reasonable wavelengths, like electrons. So let's use this equation to calculate the mass of an electron, or the wavelength of an electron. So the mass of an electron is, and by the way, this has to be in kilograms because joules has kilogram in it, and velocity has to be in meters per second. So the mass of an electron in kilograms is 9.11 times 10 to the minus 31 kilograms. And the velocity of an electron isn't fixed, so you can shoot electrons at various speeds. One that's in the book, which is like a standard way, like in an electron microscope, or a way you shoot electrons, is 2.65 times 10 to the 6th meters per second. Okay, so a couple orders of magnitude slower than light, but still pretty fast. If we calculate that out, we get 2.74 times 10 to the minus 10th meters, which is like 0.27 nanometers. So it's definitely way out in the past UV area of the spectrum. But that is a light-like wavelength. So we're saying that the electron has a wavelength kind of like a light, or kind of like light. And that's why it can behave that way. If we try to solve this for something like a baseball, it's going to be way different. So let's find, what do you think is the mass of a baseball? Anybody know? Any baseball fans? What?
Mass of a Major League Baseball.
Yeah.
Wait, how do the kilograms cancel out?
Because joules is kilogram meter squared per second squared. So the kilograms cancel one of the meters and one of the seconds and the seconds cancel, and then you're left with meters. Yeah. A joule is like a compound unit, so it's kilogram
I got something.
meter squared per second squared. Yeah,
I'm just saying an average, it's like 145 grams, just like.
145 grams. All right, so let's plug that in here.
How about fast, say like 100 miles an hour or something like that.
Oops. Well, let's do it this way. Let's say, how fast would a baseball have to be traveling to have the same wavelength as the electron, to be kind of wave-like in nature? All right, so let's say our wavelength is about like an electron, because we know electrons behave like waves when they go fast. So how fast would a baseball have to travel to also be acting like a wave like this? So we do the same thing, 6.626 times 10 to the minus 34. .145 kilograms, and we'll solve for so the speed of the baseball is going to be 2.74 times 10 to the 10th meters times 0.145 kilograms divided by so can somebody type that out for me? What'd you get?
It's pretty much exactly 6 times 10 to the 22. Like 5.996.
Okay, so we'll say 6.0 times 10 to the what?
22.
22 meters per second.
Yeah.
Okay, can anybody throw a baseball that fast?
I think anything can.
Well, yeah, well, they can't. Why?
It's faster than the speed of light mile.
Yeah, remember the speed of light is 10 to the 8th, 3 times 10 to the 8th meters per second. So this is way faster than the speed of light. Way faster, like way faster. So you could never actually get a baseball fast enough to start acting like a wave in the way that it makes a diffraction pattern. That doesn't mean that it's not and that it doesn't have a wavelength. It just means that the wavelength of a baseball is so super short that its wave properties essentially don't matter. We don't have to worry about its waves properties. It's not going to do interference stuff. Its wavelength is just too short.
But anything with a mass that moves technically has a wavelength.
Yes, anything with a mass that's moving technically has a wavelength. Yes.
Weird.
Yeah. Okay. So what does this tell us about electrons? That what are the consequences of this? So one of the consequences of this and of that measurement that we just talked about, where you're like watching the thing goes through the slit, is called Heisenberg's uncertainty principle. And the equation looks like this. Delta x times m delta v equals h over 4 pi. All right, so what does this mean? The delta x is the uncertainty in position. So that's like saying, how well do we know the position? How well do we know where something is? Do we know it within a meter? Do we know it within a nanometer? Do we know it within smaller than that? 10 to the minus 3 meters. How precisely do we know the position? M delta V is the momentum, but the delta V part is the uncertainty. We know something's mass. So M delta V is the uncertainty in velocity. So how well do we know how fast something is traveling? And if you think back to physics, what this tells us is there's a limit on how well, actually that shouldn't be an equal sign, sorry. It's an inequality. There is a lower bound for that uncertainty. So it tells us we can only know the position relative to the velocity. We can only know one of those really well. If we know one of them exactly, we can't know as much about the other one. And so this makes it what's called indeterminate, because we can't know both of those. So there's a lower limit on those. If we know the position to a certain amount, we know the velocity to a certain amount, that has to still be greater than h over 4 pi, which is a number. Now, is that a big number or a small number? It's very small. Remember, h is 10 to the negative 34. That's really small. So that means that our uncertainty is really small, which doesn't matter for something like throwing a baseball, but it does matter for something like an electron that is that small. So what does that mean in practice, or how does that affect how we can do things? It's this. So remember this from physics? Anybody do these kinds of problems? If you throw a ball that starts like at a particular speed and it's going through the air with this trajectory, then you know where it's going to land. Everybody's sort of like kind of nodding their heads. Yeah. So you can figure that out, right? Like if you launch something with a particular force and you can measure the forces and you know where it's going to land. That's called a classical trajectory. That doesn't work with electrons because of the uncertainty principle, because you don't know where it is. You can't know where it is and how fast it's going at the same time. So you end up with something like this. A classical trajectory, which is on the left, says this thing starts here, it moves through exactly this path, and it ends up here. We know where it is at every point on that arrow. An electron doesn't behave like that because it's so small, it's going so fast, that we run into these uncertainty issues. So instead, we talk about a probability distribution map, which is a way of saying the electron is somewhere in this area at any given time, but we don't know exactly where it is at each time. So it's not on a trajectory, it just sort of exists in this area. And we know it exists in this area, we know it's not in here, there's a greater probability that it's toward the center and a lower probability that it's toward the outside. And that's all we can say. It's not a trajectory, it's a probability map. So what's the consequence of that? Well, that in a second. You don't have to know this equation, but it's important, so we should at least talk about it. But, yeah.
Just out of curiosity, would it be like a continuous probability distribution on like where it will land? As in like, would you like, or would it be like discrete, like you know, like general areas?
It ends up being, well, so the function of it when you look at the actual equation is continuous. It's often thought of in this way because it's a particle. So we're like imagining an electron occupying this different spot, but the space itself would be continuous.
It just so happens that one thing that sort of
Right. So you can think of it as like a probability distribution that's greatest in the middle and then tapers off toward the ends. So what this says is when you, well here, let's define these things first. The most important part of this is this thing, psi, which is called a wave function. And this is an equation that can describe the behavior of an electron. We're not going to get into the details of that, but it's a parametric equation, which means it has parameters, has different bits to it, and we are going to talk about some of those. And it fits in this equation. And so a wave function that is a solution to this differential equation is one that, when operated on with this H Hamiltonian operator, produces these energy levels. So anybody here good at differential equations? I don't know if that's like a thing that you like, but maybe soon you'll be in those classes, I don't know. But it's saying that like as this thing changes, right, something else changes, And so wave functions for which this works are wave functions that can describe these electrons. Now, for our purposes, we need to know a couple things. One, that the wave function depends on 4 parameters, and these parameters are called quantum numbers. Secondly, that the square of the wave function is a probability distribution for an electron in an atom. So if we find this wave function thingy, which is just literally a function, it's like a mathematical function that has these different parameters in it. If you take that and you square it, you graph it, you get the shape and the picture of where an electron could be in an atom. It's important that that's a probability distribution because of the uncertainty principle. We can't know exactly where the electrons are in the atom. And so that's really the big problem with the Bohr model. Remember the Bohr model up here? Bohr knew that his model wasn't quite right because it failed in a couple ways. But this is one big problem, is this model violates the uncertainty principle. If you imagine electrons traveling in an orbit around the nucleus, that violates the uncertainty principle. Because just like our planets, if you think about the planets in the solar system, we know exactly how fast the planets are going. We know their trajectory. We can calculate where they are at any given time. Electron, you can't do that because that violates the uncertainty principle. So that's a problem with the Bohr model. The other problem with the Bohr model is it only works for atoms with 1 electron. How many of those are there? Well, yeah, and unless you have some ions, but yeah. So that's another problem. But it violates the uncertainty principle. So we know that we need a better picture for how electrons exist within an atom than that they're in these rings, because that's not right. They're not in these orbits. They don't orbit the nucleus like planets. That's not right. All right, so we can start to figure this out by solving the wave or graphing the wave function using these different parameters. And what we get are these different shapes. So let me show you the shapes, and then we'll go through the quantum numbers and talk about what that means. So if you put a certain set of parameters in this wave function and you square it, you get this probability density. And so this tells us that one place that these electrons can be, if these electrons are described by a particular wave function with particular parameters, is basically a sphere. So the probability distribution is a sphere. And as you change the parameters, you get some pretty weird different shapes. These, again, are probability distributions. So these are where the electron could be if it's described by these particular equations. And we have different names for those. So I'll just show you those for now. Let's talk about these parameters, which are called quantum numbers. There's 4 quantum numbers, so we'll go through each of them. The first one is n, which is the principal quantum number. And this one we already kind of know. This is the good old energy level quantum number from the Bohr model. And it starts at 1 and goes up in integers as far as you want. There's infinite levels. So as you go up in energy, you increase your principal quantum number, and these are the different levels that we've just been talking about that the electrons can jump through or whatever. So that's one of the parameters in this wave function equation. The next one is called L. L is known as the angular momentum quantum number, or the azimuthal quantum number. We'll call it the angular momentum quantum number. And this tells us something about the shape of those areas. It's called angular momentum, has to do with motion in this kind of a direction, right? Motion in a spherical sort of direction or a curved direction. So that changes the way that the electron can be inside the orbital. And sometimes we call this the type of, and we're going to use a new term here. I know I just used it, but orbital. Notice I put a couple of letters on the end there. Orbit means something going around a middle body, like a planet orbiting the sun. We just talked about how those orbits don't apply to electrons. They don't work like that because that violates the uncertainty principle. So instead, we use the term orbital, which is kind of like something like an orbit, but not quite. Because these electrons can actually have very different ways of moving around depending on what type of quantum numbers they have. So L can be anything from 0 to n minus 1. So the L is limited in the numbers it can have by the n number. So if you're an electron that you have you're in the n equals 2 energy level, that means you can only have 2 different L's possibly. You can have L equals 0, you can have L equals 1. If you're in the n equals 1 level, that first level, you can only have one possibility for L, which is 0. These are also, because they're important like this, they're given letters. So L equals 0 is known as an s orbital. L equals 1 is known as a p. L equals 2 is known as a d. L equals 3 an f. And that's all that really exists in the atoms that we know, but theoretically it could keep going. All right. Third one is known as ML. Okay. Which is the magnetic quantum number. This one specifies the orientation of the orbital, so like which direction is it pointing? It can take values from negative L to positive L. Well, maybe I should put a little, make it a script L or something so it doesn't look like a 1. So again, that means it depends on the number before it. So when you got your n number, if you're an electron at a certain energy level with a certain n, you have a certain choice of L's. Once you know what L you have, then you have a certain choice of different MLs that you can have. And then finally, last one is ms. It's called the spin quantum number. And it can only take two values ever. It's either +1/2 or -1/2. And it's called the spin quantum number because it describes this property called spin, which originally was thought like the electron could spin one way or spin the other way. Now we know it's a little bit more complicated than that, but we still call it the spin quantum number. We still talk about the electron spin. All right, so how do we use these things, or what do we do with them? Let's go back to those pictures and talk about what this looks like. So here's what we call a 1s orbital. A 1s orbital is what you get when you solve that probability distribution, that psi squared, and you plug in n equals 1, it's the 1s, so your n equals 1, and then L equals 0, because 0 is associated with s. So we call that a 1s orbital. If you graph that probability density, you get this. So that says that an electron with those particular quantum numbers is going to be somewhere in this area in the atom. The middle is the nucleus. It's going to be somewhere within this sphere. All right, so let's change that now. Let's bump it up to n equals 2. Where can an electron be in the second quantum shell, in the second quantum number, in the second energy level? Oh, this one's small. We're going to have to zoom in a little bit here so we can see it better. Here's what a 2s probability distribution looks like. It's still spherical, but now it actually has this thing called a node in the middle, which is an area of 0 electron density. So that means that the electron could be anywhere in that blue sphere except for this little shell in the middle, which introduces some kind of weird stuff. If we look at the graph here, this is called a radial probability. So look at the bottom one here. That's the nucleus. So there's 0 probability of an electron being in the nucleus. Then the probability increases. Then there's another spot here where there's 0 probability of an electron being. Then it's probably mostly here, right? That's the highest probability. And then it fades out toward the end. That's weird because that says that an electron is sometimes here and sometimes here, but never actually travels between them. So it's here, but it's never in between. And so that's what you get if n equals 2 and L equals 0. But maybe remember that L can take values of 0 and then all the way up to n minus 1. So if n is 2, what's the maximum L value that we can have? If L, but 1, because it can be anything up to L n minus 1. N is 2, so the biggest L has to be 1. So what happens if instead of L equals 0, we have L equals 1? Well, now that probability density changes drastically, and you have what we call the p orbitals. So instead of a spherical type distribution, you have this kind of dumbbell-like distribution where there's a node in the middle, an area of 0 probability in the middle, and then you've got these lobes of density on either side. Because it's not spherical now, we can also have different orientations. So if we go back to our quantum numbers, we've got now n equals 0, or n equals 2, L equals 1, which means ML can be anything between negative L and positive L. So if L is 1, then ML can be what? What are the different possibilities for ML? It can go anywhere from negative L to positive L. So if L equals 1, ML can be negative 1, 0, and 1. So there's 3 possibilities for ML. And that's what? They're always whole numbers, yep. And so depending on how we plug that in, we get 3 different orientations of p orbitals. They all look the same, but they go different directions. Another thing to remember here is we can't specifically assign ML to specific orbitals. In other words, we can't say ML equals -1 is the PZ orbital, ML equals 0 is the PY orbital, and so on. Any idea why those don't go like that? It's because the axis assignment is arbitrary. So we can pick whatever direction we want Z and X and Y to be because we're just talking about an atom. So we can't say like this quantum number applies to this one and this quantum number applies to this one. There's 3 possibilities, there's 3 orbitals. So the most useful thing about ML is just that it tells you the number of individual orbitals you have in a particular, what we call a subshell or an L level. So we say, let me give you an example of how that works. We say L equals 1. How many orbitals are in the L equals 1 level? Well, you say, okay, well, it can take ML from -1 to 1. So that's -1, 0, and 1. So there must be 3 orbitals in the L equals 1 level. See how that works? How many orbitals would be in the L equals 2 level? Close. What? 5. See that? So if L equals 2, then ML can be -2, -1, 0, 1, or 2. So that's 5 different orbitals. And they get even weirder looking. These are the d orbitals. So depending on which ML you have, not only do they change their orientation, but they can actually change their shape entirely. And this one of the lobes is like more kind of looks like a p orbital, and the other kind of makes a donut around the middle. And then if we go to the f orbitals, what would be the L number for the f orbitals? You can figure out by how many there are. So there's 7 f orbitals, so what must L be? 3, yeah. Because that means ML can be -3, -2, -1, 0, 1, 2, 3, which is 7 different orbitals. All right. Okay, so let's practice this. I didn't print them out today, but I put this document in the notes folder, so some more practice problems from the chapter 7 stuff. Let's jump down and look at some of these quantum number things, and then we'll go back on next week and get some of the other stuff. Okay. We'll talk about that MS, that last quantum number, more in the next chapter too. So here's the type of problem for using these quantum numbers. Which of the following is a correct set of quantum numbers for an electron in a 3D orbital? So how do we figure this out? Well, first of all, what is the easiest one to determine? What do you say? If you're in a 3D orbital, what's your principal quantum number? What level are you at? Which n level? You're at 3. So that's always kind of the main first one. It's always shown, it's always given. We're at the third level, n equals 3. So now L, how do we find L? Not quite, because remember, well, L can take different values up to n-1. That doesn't mean it's always n-1. But it does tell us, so one thing we can do with that is we can eliminate D. Because L can't be 3. The biggest L could possibly be in the n equals 3 level is 2, because the biggest value it can take is L-1. So it can either be 0, 1, or 2. And to figure that out, we actually just have to know these types of orbitals. So we have to know that 0 is S, is called S, 1 is called P, 2 is called D, 3 is called F, and 4 is called G. There's not a good way to like figure that out. But now that we know that, a D orbital has to be L equals 2. So it's got to be C. Let's try another one. Which is a correct set of quantum numbers for an electron in a 5f orbital? So which ones is it definitely not? C and D, because those would be a 4 something orbital. So is it A or B? A, why A? Yeah, because L equals 3 is an F orbital, L equals 2 is a D orbital. So it's got to be A. Whoa, this one didn't come out right. But it's a good question, so let's see if we can fix it. So this, we'll just rewrite this over here. Okay. So if we're looking at a hydrogen atom, which of the following combinations of numbers is not allowed? We'll say that's A through E. Which is not allowed? Which is not a possible way to describe an electron? Everybody see it? E? Why? Right. You can't have, yeah. So you can't have L equals 3, because the biggest L can be is n minus 2. Are there any more of that style? The following combinations of quantum numbers are not allowed. Correct each set by changing only one quantum number and write in an appropriate corrected value. So for the first one, it says n equals 2, L equals 2, ML equals 2. How could we correct that by changing only one number? I think I heard it somewhere. Yeah, we have to bump this up to 3. See that? Because in the n equals 2 level, we can't have L equals 2. But if we change that down to 1, then we couldn't have ML equals 2, because ML can only go from plus L to minus L. If we bump that up to 3, then we're good. All right, what about B? Which one should we change there? Yeah, we should change this one to whatever we want, but something positive. So maybe we'll just change it to 2. L can't take negative values. So for the following orbitals, state the sketch showing the shape and orientation of the orbital. So a 3s orbital what are the 3 quantum numbers that it should be here? What should n be? 3. What about L? 0. The s orbital is 0. And what about ML? It's only one choice for ML in this case. It's got to also be 0. ML goes from negative L to plus L. If L is 0, there's only one choice for ML, 0. And what does it look like? Yeah, that's going to be a sphere. However you want to draw a sphere. It's spherical. What about the 2px? What's n? 2. What's L? The 1. The p orbitals are 1. And what about ML? Yeah, ML can take 3 different values here. So in this case, it says state the values which apply. So I don't know if it wants you to like pick one or just say that it could be any of those three. We don't know. It could be any of those. And then a p orbital is going to have that shape like this. Because it's the px, what does that tell you? It's on the x-axis. So we can pick our axes however we want. I would just say that this is x, and this is y, and that's z, right? Does that fit the right-hand rule? Yeah, I think so. And then that makes it a px orbital. Okay. All right, we've got a couple minutes left. Let's check out some of these other questions. We didn't do an example of this one, so let's try this one out. According to the Heisenberg uncertainty principle, if the uncertainty in the speed of an electron is 3.5 times 10 to the third meters per second, the uncertainty in its position in meters is at least, so we have to look at that equation again. The nice thing about these types of questions in this class is, you know, it's not a calculus-based class, so we're not going to do all the really crazy math that's involved in quantum mechanics. So all the math type stuff from this chapter is just plugging stuff in equations. So you have the equation, you plug the stuff in there. These equations would be given to you on the exam, although they won't be named, so you'd have to know that this is the equation for the uncertainty principle. So if the uncertainty in the speed is 3.5 times 10 to the third, that means we're going to solve for x. And we'd have to look up the mass of an electron again, which is times that uncertainty in position, or in velocity. I'm going to need a little more math power to do this one, I think. Figure this out. Oh, yeah, I'm sorry. No, you're right. Yeah, of course. Should be h over all that stuff. Thank you. Let's put these numbers in and see if it works here. Oh, it doesn't like h? Okay. All right, so assuming we did all that right, what is that? 1, 2, 3, 4, 5. I get 10 to the minus 5. Did I do something wrong? Oh yeah, so this is supposed to be 34, not 31. That's better. Okay. So what does that mean? That means that if we have a pretty large uncertainty in the velocity, right, plus or minus 3,500 meters per second is a pretty big unknown. That means that we can know the position very precisely, down to the about 17 nanometers, which is still, again, 17 nanometers is much, much bigger than an electron. An electron, or than an atom. An atom, size of an atom is about 0.1 nanometers. So even if we have huge uncertainty in the velocity, we still don't know exactly where the electron is inside the atom. All right, that's about it. Other questions, come let me know. Otherwise, have a good weekend. Congratulations on being halfway done with class. And yeah, start up next week.
Chapter 5 quiz on you?
Yeah, so chapter 5 quiz on Monday. Just chapter 5, just gas stuff. Yep, thanks.